So in this short video, I will talk about the optimization problems, which will be oftenly used in all kinds of the machine learning algorithms. So optimization problem. First, I want to get you familiar with the types of the optimization problems that can be solved readily and relatively efficiently, and the names of some of the optimization algorithms used to solve them. An important skill for you to develop is be able to go from an application to a well-defined optimization problem. That skill depends on your ability to recognize well-studied types of optimization problems. So you apply some machine learnings, but you need to be able to solve those problems, solve those models, how to fit that models to your data. Okay, the first type of the optimization problem is called unconstrained optimization. So first type is unconstrained optimization. So the example we already see before is for example, uh, the first classification machine we introduced in the second video, the second lecture, is called perceptions. Perceptions. Remember, in the perception classifier, what we need to solve is we want to minimize the risk. We need to solve the classifications using the W vector. We want to minimize this, right? We want to minimize this, and this where this R, this risk is the summation of the loss, right? Summation of the loss at each point x. So we minimize this function, we get our solution. So without any constraints. So here, in general, this unconstrained optimization, the goal is to find a W vector that minimizes we want to minimize this, or later on we talk about the maximum likelihood method. We maximize to maximize a continuous objective function. For example, the fx or f omega. We solve the weight. Usually we want to solve a smooth function f. So here, what a smooth means? Smooth means the derivative is continuous too. The derivative, the gradient. If you have the vector, it's a gradient. Is continuous. And So there are two types of the problem. One is called global minimum. Okay, which means we want to find a greater minimizer. So which means we want to find a W star such that f at any other point will be greater or equals to this omega star. Okay, this is our solution for all W. Okay, and the local minimizer, local minimum. So in other words, we found find this for we don't have for every. So here I can give you some example. For example, if we had just one-dimensional function, so one-dimensional features, suppose our function looks like this. So this one and this one will be local minimum. And this point, I'll use different color. This point will be W. Let's say this function f is minimized at this W star. This W star is a global minimum. So this is a global minimum. Global minimum. Okay, so it's lower than any point, but the local minimum is just lower than any points in the neighborhood of these W's. Okay, I need more space here. And usually the local minimum is easier. And the global minimum is often hard. Later on, when we introduce, for example, the deep learning neural network, we have the hundreds of the parameters, features, and the parameters you need to solve minimize that loss. So you are minimizing a function with 100 or few hundred dimensions. So in that case, it's really impossible to find the global minimization. But there is one exception. Okay, the convexity. So a convex function always has global minimum. So here, what's a convex mean? Convex means okay, maybe let me give you a definition here. F is convex if for any points x and y, the linear combinations of this x and y will below, so for example, the x plus beta times y will below the fx plus beta fy minus fx. The direct interpretation is, for example, if quadratic function is convex, because so suppose we have the quadratic function here, and now if you apply any point, 2 points x and y, x and y, and you connect them, so this, and you pick any point on this line segment, so this point will be at x plus beta y. Okay, so this means, and fx plus beta y should be bigger than the point here. So the let me rewrite this. So this is f x plus beta y. Okay, and any point, this point will be equals to the weighted average between fx and fy, right? So this will be fx plus beta fy minus fx. Okay, so in other words, if we had a parabola here, any two linear combination values, so the line segment is above the values at this point So if that's the case, we have the global minimizer. I think the geometry intuition is very clear here, right? Okay, so, and wait, this beta should be between 0 and 1, right? If you have the beta is 0, if it's fx, if it's beta is 1, sorry, this is the formula is a little bit wrong here. This is beta x minus y minus x. Okay, so if you pick the beta equal to 0, so we don't have this term, we're gonna have x, right? If beta is 1, we have y, right? So beta equals 0 is this point. Beta equals to 1 is this point. And then when beta arrange from the beta equals 0, beta equals 1, we get all possible points in between. And for any points on the line segment is higher than the function value at that point. So that is what convex means. So for those cases, we always have the global minimum. Okay, and the convex function has many good properties. For example, good properties of convex function. First one, the sum of the convex function is also a convex function. For example, when we solve the for example, when we solve the perception problems, so this law, each of the laws actually is convex, and the summation is a risk. So this risk is a summation of the loss. So this risk function is also convex. Okay, I may not write here. Second, has just one local, if f is continuous, minimum is unique. There's only one minimum. Or connected set of local minimum. Connected set of local minimum. That are all global minimum. For example, if you go to the previous lecture, we have one problem. Do you remember if we have a classification with only 3 data points, the minimizer, that function is perception minimize the risk function here, right? And that function is continuous, and we have the connected set, which are all the minimizer for this problem. Okay, so those are good properties of the convex function. And also the first algorithm we're gonna talk about is the gradient descent algorithm, right? Gradient descent algorithm. Or maybe I will talk more in next video.